Excuse me, do you have a moment to talk about engine cooling? Today I'm going to be pulling the cooling system out of my C10 and replacing it with this brand new PWR radiator. But before I do, I want to explain to you why I chose this radiator. And I promise, it's not all the good looks. There's some proper science and math to back up the decision. We're going to talk about how radiator technology evolved, how aluminum changed everything, and then we're going to walk through the heat transfer equation necessary to understand the cooling capacity that your engine actually needs. And then I'm going to install this thing, so let's get to it. This radiator core in my C10 is probably what most of you grew up seeing under the hood. Copper and brass core, but now in the 70s, 80s, and 90s, mass manufacturers shifted to plastic tanked aluminum cores because it was cheap to manufacture and it was easy to repair. You'll see that these plastic tanks are crimped onto the core with a rubber gasket. That seal is the Achilles heel of the design. Heat cycles, heating up, cooling down, heating up again, cooling down again, causing the plastic to fatigue over time. Eventually, this gasket weeps, the plastic cracks, and then you end up with a leak. But finally, the big comparison to the other radiators from before is that this PWR radiator sitting next to me is all aluminum. Be it the mounts on the top, the fan shroud in the back, or the core that's sitting here in the middle, every square inch of this is aluminum, and that's really where the advantage comes in. Now, PWR being more or less founded in that motorsport, supplying NASCAR, IndyCar, Formula One, trophy trucks and the like, that same engineering ideology is really transferred down the line into the aftermarket products as well. Now, while I can appreciate this starts to sound a bit like a marketing ploy here, I do want to kind of focus on a couple of the big differences between these two units and how far things have come from like OEM replacement type units like what's in front of me here versus what PWR does. You can see down in this tube, this inlet here, it'll focus, that those are round cylindrical type tubes. And the water going through there, you can imagine that there's not a lot of boundary layer touching the outside of those tubes and transferring heat with the air around it, where something like this PWR radiator has a long flat tube that goes from the front to the back face, and this is not cylindrical. This is a bit of an oval shape on this end coming in, and these are actually dimpled, allowing the fluid going through here to break up, spin around, and mix, allowing it to exchange heat better with the oncoming air of the fin. So then another point we want to focus on here is you can see the difference in the fin itself. This geometry is very simple, and there's not a lot breaking up the air that's actually going through these tubes and these pieces of aluminum. Now, big comparison here, the PWR radiator, you can see, and this is very similar to OEM radiators that you would find in newer vehicles today, that this fin has this louver shape cut into the pieces of aluminum, and that helps break up the airflow going through these fins and exchange heat better with the fluid that's going through the tubes. So if you look very closely at any given fin here, you can see those little cuts in the fin. So when looking at the differences between these two units, you can start to really understand how far technology has come with the aluminum radiators that started versus what we have now. So obviously this not plastic tanked unit's going to hold up a lot longer than something like an old OEM may, or really, as far as things have come today, a lot of units actually start to look like this one, where they do have dimpled tubes and they do have louvered fin. However, with plastic tanks, and if you're using it in any sort of racing application, you're taking your brand new car out on the track frequently, and it's not just going down the street every day. When you start to pump that heat into your vehicle on the high end of cycling and you're pushing it outside that standard OEM window, you really want to start looking into something like a proper aluminum radiator. All right, so this is actually my favorite part of the video. Most radiator sizing advice comes down to bigger is better and here's what fits. But let's be far more precise than that. We're going to use the fundamental heat transfer equation, Q is equal to m dot c dot dt. Right? So this is one of the most useful equations in all of thermodynamics, and it's really not that complicated. So let me walk you through what each of these terms means. Q, this is thermal power. This is the rate at which heat energy needs to be removed from the system, and I'll express this in kilowatts. You can express it in BTU per hour and then convert to kilowatts, but we're going to use kilowatts. M is mass flow. This is how much coolant's moving through the system per second. A typical engine-driven water pump at mid RPM moves somewhere between 20 to 40 liters per minute. So that is your mass flow rate. C is the specific heat capacity of the coolant. For a 50-50 water and ethylene glycol mix, that value is approximately 3.4 kilojoules per kilogram per degree Celsius. So 3.4 kJ per kg per degrees C. Pure water actually has a better heat transfer number here at 4.18 kJ per kg per degrees C. However, obviously, I'm not running pure water in my truck. It's going to be run in the winter and other times where corrosion and a mix for freezing is a little bit more important. And then lastly here, DT is just the temperature differential between your inlet and your outlet. So inlet minus outlet is your DT. So if it comes in at 210 and it leaves at 180, your DT is 30. All right, now let's plug in some real numbers for an LS. Let's take an LS1 at the baseline here. A stock LS1 at wide open throttle produces somewhere between 250 and 280 kilowatts at the crank. Let's call that 350 horsepower. And just in round numbers here. Internal combustion engines are only about 30 to 35% thermally efficient. So 30 to 35% efficient, right? A reasonable rule of thumb is that roughly 25 to 30% of your total fuel energy ends up in your heat rejected to the coolant. So let's spell this out here. 280, so I'm going to pick the top end of the kilowatts here, divided by 33%, is equal to 850 kilowatts. So that is your thermal efficiency, somewhere in the middle of your thermal efficiency here. You're dividing your kilowatts at the crank and you get this number. Now I need to figure out what is going into my coolant, and I want to take somewhere between 25 and 30. So if I take 28% of that, I get 240 kilowatts going to the coolant. So this, at wide open throttle, is what a radiator would need to reject. However, our radiator is not always going to be rejecting heat at our wide open throttle, and that's not the design point of our radiator. So let's walk through what an engine will actually reject somewhere in the cruising and somewhere in towing. All right, so let's walk through our two scenarios here. We got cruising and towing. So let's start with a highway cruise at 70 mile an hour. At a 70 mile an hour steady state on flat ground, a C10 with an LS engine is producing somewhere between 40 to 50 horsepower to the wheels to overcome aerodynamic drag and rolling resistance. So let's call that 35 kilowatts at the crank, right? And that's a fairly generous estimate. And we're going to run the same fuel energy budget that we just did on that first slide. So 35 divided by 33% is equal to 106 kilowatts. And now the heat transfer to the coolant is 28% of that. So we take 106 and multiply that by 0.28 and you get 30 kilowatts. So this, at highway cruising, you can see my radiator only has to reject 30 kilowatts of heat. And that's an eighth of your wide open throttle figure. And that is why a stock radiator survives daily driving for 20 years. It's not being asked a lot of your radiator. 30 kilowatts is a very low heat rejection target, especially when just running down the road. This is very achievable for even those really old radiators. Now our second scenario here, towing, this is where it gets a little bit more interesting. So let's say you're towing 5,000 pounds up a 6% grade. Think about a mountain highway on-ramp at 55 miles an hour. Now that engine might actually be working at 150 to 180 horsepower sustained. So say that's 130 kilowatts at the crank. So let's do this same equation that I did up here. So we got 130 kilowatts, and then you divide that by your 33%, and you get 394. And now you take your 394 and figure out the portion that's going to the coolant by multiplying by about 28%, and you get 110 kilowatts. So now this is 110 kilowatts sustained, and that's what makes towing so much harder than even track days in some ways. On a track, you're just at wide open throttle for a few seconds at a time, but towing 60 to 70% throttle for minutes, and the Radiator doesn't get a break. Airspeed is lower on the highway cruise because you're moving slowly up a grade, so you have less ram air than pushing through the core than something like a track day, and ambient temperature might be 35 degrees in the middle of the summer. So this is the condition that kills marginal cooling systems. It's not the drag strip, it's the summer mountain pass with a trailer. All right, so I got three conditions here. I got 30 kilowatts while I'm cruising. I got 110 kilowatts while I'm towing uphill. And then I got 240 kilowatts at wide open throttle. So you can say that if I can get a radiator that'll comfortably deal with 110 kilowatts at, maybe 15 minutes or 20 minutes. Now, yeah, my temperature might climb a bit if it's really hot outside, but it's not gonna overheat my engine by any means. I'm not gonna be at wide open throttle every single second that I'm driving this, and it should very easily be doing that 30 that I'm looking for while cruising. This should be something you should consider when sizing a radiator. All right, let's tie this back to the radiator and that first equation that I made. All right, so we had a pump flow at say 30 liters per minute, and that's equal to 0.5 kg per second. That's of coolant flow. My specific heat is 3,400 joules per kg per degree centigrade. Now, what do I need to do in order to reject that 110 kilowatts? What's our DT needed in our Q is equal to m dot c dot dt. If I've got a flow and I've got a specific heat capacity and I've got a heat rejection here of 110. So let's find out. So we get 110 is equal to 0.5 kg per second by 3,400 joules per kg degrees C. And then you're solving for delta T. So what do you get? dt is equal to 65 degrees C. Now, if you're talking about an inlet versus outlet temperature of 65 degrees C, if I have an inlet temperature of 100, bringing that temperature at the outlet side down to 35, well, if I've got a low ambient temperature outside, or I actually start messing around with our water flow rate and we start bringing this up, which now lets me bring my overall temperature down, you could see how this 110 kilowatts is actually really achievable with just a stock LS engine. You can really push this kind of power out of this radiator, and it's not a big deal here. So, however, with wide open throttle, you could see that if I need, say, my 240 kilowatts and that's at the same flow rates here, 0.5 times 3400 times a dt. My dt here is actually going to be 141 degrees C. And if my inlet temperature is 100 C, you're not going to get an outlet temperature that's, especially if your ambient temperature is 35, you're not going to get anything below 35 if you're perfectly efficient. So you can see that at wide open throttle conditions, this is physically impossible. You're breaking laws of thermodynamics here. You can't do this with this radiator in this case. So that's why it's really important that you size it for the condition that you're doing it for and understand the effect of, say, holding it at wide open throttle. So with confidence, I can say that I know my PWR radiator is going to do what I want it to do. It's gonna hold up for cruising very easily. I know we're gonna be good towing up a hill right in the temperature range that I want it to be. And wide open throttle, well, if I lay on it and do burnouts, I should still be all right every now and then. I'm not worried about this. Low time variation conditions, not worried about this kind of situation. I know the PWR radiator is going to do it right for me. And this math tells me exactly what I need to know about my upgrade here. Well, now it's time out with the old, in with the new. One of the first things I did, however, was I cut a 7-foot length of wire and held it to the edge of my radiator here to make sure that I can run transmission lines from this side of the cooler back to my transmission, because the new cooler I have has transmission fittings and the transmission cooler on the opposite side of OEM. So I'm not going to be using OEM lines anymore. I'll be using AN lines, soft braided lines, or some sort of rubber line to run back to the transmission. All right, so first things first, I need to jack this thing up and then need to take the rubber hose off the bottom end of the old radiator. And hopefully this will come off easily. Well, you know what? Before I'm too dumb, this actually has a drain petcock in it. So I think I'm just going to put the bucket under there before I go dumping everything out of this hose. I've got a bunch of coolant all over my floor now, but it is what it is. Let's get some hoses off of this thing and get this radiator out of here. All right, so one of the last things I needed to do before I get that radiator out of there is I wanted to crack these couple of trans lines loose so that I can pull the trans lines off the radiator as well, get these out of the truck, and then replace them with aftermarket lines. All right, trans lines are cracked from underneath. Gonna lower this down a little bit and then crack the lines off the radiator. All right, let's get these radiator mounts off and then get this thing out. All right, so radiator's out, but first things first, I want to get these lines out. I'm going to put this back on the ground and then I'm going to clean up all this garbage coolant everywhere. So get this a little spiffied up and then I'll take this fan off and we can fit up the PWR radiator and see how it fits. Sweet. All right, so engine bay's all cleaned up. Trans lines are gone, cleaned up the coolant and the ATF, and then I pulled the fan off the front end of that pulley there. So it's time to put this down in there and test fit it up, and then I'm gonna call it for today. All right, my radiator's in. Test fit's done, things are cleaned up, and I've got a list of stuff to do. I've got trans lines on order. I need to start sorting out what kind of rubber hoses I want on the top and bottom end since they don't quite match up. And then from there, I need to finish the wiring and get the engine running again so that I can fill it up with fluid. That being one of the biggest points, on any project car, you don't want to fill the radiator with fluid if it's just going to sit around. You'll corrode the inside if you haven't yet turned it over, heated it up, and actually passivated the radiator. Make sure that if you're going to do what I'm doing here and test fit and just leave it sit for a while, that you don't just fill it up with fluid and let it sit. That's going to do it for now. And here's where I tell you one other thing. I spec radiators for a living. I work at PWR in the motorsports department doing exactly what I'm doing here. Taking the math behind what a radiator needs in a vehicle and then determining what spec, size, shape, fitment looks like for all of these motorsports teams across a large variety of different vehicles. If you've got questions, hey, leave a comment. I might be able to help you out. And as I said before, if you've enjoyed watching me wrench on this thing, that's awesome. I'd appreciate you following along. Till next time.